In an isobaric process or a constant pressure process, a gas is heated at constant pressure. So, because of this, as we can see, the temperature of the gas increases and the volume of the gas also increases. So, there is change in temperature and change in volume. And therefore, this process is going to have work done because of the expansion of the gas. So, work is done by the gas as we are heating the gas. Let's visualize the process using a pressure volume diagram. So from state 1, the gas expands to state 2 at constant pressure. So as we can see here, the pressure is not changing, that is P1 is equal to P2, and the volume is increasing, that is the gas is expanding from V1 to V2. And since there is a change in volume, there is an area under the graph that represents the work done by the gas. All the thermodynamic properties at state 1 are represented with a subscript 1, that is pressure P1, volume V1, and temperature is T1. And at state 2, all the thermodynamic properties are represented with a subscript 2, that is P2 for pressure, then V2 for volume, and T2 for temperature. To derive various thermodynamic properties that undergo changes during a constant pressure process, let's begin with the pressure, volume, and temperature relationship. From the characteristic gas equation, we know that PV by T, that is pressure volume product by temperature, is equal to a constant. So by applying the states, we can rewrite this equation as P1 V1 by T1 is equal to pressure at the second state, volume at the second state, divided by the temperature at the second state. And since this process is a constant pressure process, so pressure at state 1 and pressure at state 2 are going to be the same. So this equation will become V1 by T1 is equal to V2 by T2. Or we can rewrite this as volume 1, the volume at state 1 divided by volume at state 2 is equal to temperature at state 1 divided by temperature at state 2. The work done in a constant volume process can be given by integral of pressure into small change in volume. This can be rewritten as by taking the constant outside, that is pressure, into the change in volume, and therefore this is going to become pressure and volume, lower limit and upper limit. So we can finally write this expression as pressure volume product at state 2 minus pressure volume product at state 1. That is P2 V2 minus P1 V1. And since PV equals MRT, we can rewrite this expression as work done is equal to M R times the change in temperature. The change in internal energy can be given as del U is equal to mass times the specific heat at constant volume into dt, or this can be rewritten as mcv integral of dt, or finally the internal energy can be simplified as del U is equal to mcv times the change in temperature, that is T2 minus T1. To derive the heat transfer during a constant pressure process, we can use the first law of thermodynamics, which is Q is equal to work done plus the change in internal energy. We can rewrite this expression by substituting the values of work and internal energy, that is M R T2 minus T1 plus M CV T2 minus T1. Since the gas constant R is equal to Cp minus Cv, so we can rewrite this expression as Q is equal to M Cp minus Cv times the change in temperature plus M Cv times the change in temperature. So we can simplify this expression further and we can get MCP T2 minus T1 minus M CV T2 minus T1 plus M CV T2 minus T1. And as we can see, the common factors can be cancelled out, that is minus MCV T2 minus T1 plus MCV T2 minus T1 can get cancelled, and finally we get the heat transfer is equal to mass times the specific heat at constant pressure times the change in temperature. The change in enthalpy in this process can be given as del H mCp dt, so which can also be rewritten as mCp or mCp T2 minus T1. So as we can see here, the change in enthalpy in constant pressure process is equal to the heat transfer. This is because if we take enthalpy, that is change in enthalpy is equal to change in internal energy plus pressure into change in volume. And in this, if we substitute the work done, so this expression is going to become Q plus pressure volume minus pressure volume. So therefore, the change in enthalpy is going to be equal to the heat transfer.